Hello viewers, and welcome once again. We are still under logic, Christ Almighty God's algebra. Today we are going to treat law of complement. Law of complement, we have law of complement by conjunctive statement and law of complement by disjunctive statement. But we're going to start with law of complement by conjunctive statement. Let us start. Law of complement. P and not P is equal to F. This is a typical example of law of complement by conjunctive statement. Why do we call it law of complement by conjunctive statement? It's because of this and connective that combines P and not P together as a statement. So it is called conjunctive statement. P and not P is called conjunctive statement because of this and that combines them together. It becomes conjunctive statement. So that's why we call it law of complement by conjunctive statement. So if you look at this equation, you will find out that it is logical equivalent. That means it is law. Because whenever the left hand of the equation is true, then the right hand of the equation must also be true. In the same vein, whenever the right hand of the equation is false, also the left hand of the equation must also be false. We say that it is logical equivalent. But in this case, there is no variation, there is no variable of truth value in this equation, because P and not P, when you evaluate it, it will give us constant F. The same thing here, F remains F as a constant. So whenever P and not P is F, then this F is also F. In the same way, whenever this F is F, then P and not P is also F. That means contradiction or falsity. So let us prove this statement that it is law of complement. Proof. Suppose P and not P is equal to F. We assume that the statement is true. That means P and not P is equal to F is true, and is our hypothesis. If you look at this statement as explained earlier on, that P and not P is always validated to be F, constant F. The same thing with F, always F. So we see that whenever P and not P is F, also F is F. Whenever F is F, also not P and not P is also F. So since it is logical equivalent, we can transform it to biconditional statement. That is, if and only if P and not P, if and only if F. Now we have not transformed it to biconditional statement. So whenever P and not P is F, that means the left equivalent is F. Also, the right equivalent is also F. Whenever the right equivalent is F, also left equivalent is also F. So whenever we want to validate statement, there's no possibility of getting falsity, always truth. We say that it is tautology because if F is T, so we say that it is statement is tautology, being justified by logical equivalent. Being justified by logical equivalent. If and only if and only if. Now, since this statement P and not P, if and only if F is tautology, we can also transform it to conditional statement and it will still preserve tautology. That is, P and not P implies F. And whenever the antecedent of the statement is true, also the consequence must also be true. But in this case, there is no possibility of getting falsity in relation of the P and not P. Always, so there's no possibility of getting T. We evaluate P and not P. Always F. And here is also F constant. So F implies F is always validated to be truth. So in this statement, there's no possibility of getting falsity when you validate statement always truth. We say that statement is tautology. Is tautology being justified by logical implication. Now you will find out that P and not P implies F is tautology. C is tautology, it means that P and not P, the antecedent, is proper implication of the consequent F. And if it is proper implication of the consequent F, I mean this P and not P, the antecedent, is proper implication of the consequent, we say that it is certain that P and not P, the antecedent, exists. And if it's certain that it exists, if it's certain that P and not P, the antecedent, exist, we say that P and not P, the antecedent, is logical implication of F, the consequent. If and only if P and not P is logical implication of F. P and P is logical implication. Let's set it very well. Is logical implication of F. You have seen that you have now deduced that P and not P is logical implication of F. If this is true, also this must also be true. So if and only if P and not P is equal to P and not P, So it is true that the logical implication is equal to itself. Logical implication is equal to itself. It is true. Because whenever the left side of P and not P is true, is false, because it's always better to be false. Also, the right hand side of P and not P is also false. Whenever the right hand side of P and not P is false, also the left hand side of not P and not P is also false. We say it's logical equivalent. It is true that it's logical equivalent. Being justified by identity, the sameness. Being justified by identity. So if and only if P and not P is equal to, you will see that this P and not P is always related to be F. Is always related to be F. Since it's always related to be F, is equal to falsity. And it is equal to F. So when you evaluate it, it always gives you constant F. If it's always given constant F, you say that the statement is contradiction, that is F. So P and not P is equal to F. Being justified by contradiction. We have done contradiction in our previous tutorial, so you can go back to our previous tutorial to be acquainted with knowledge of contradiction. Now we have proved that P and not P is equal to F. See, it is equal to F. Now we then conclude, say thus P and not P is equal to F. We know that the statement is logical equivalent. That means P and not P is equal to F is logical equivalent. Since it's logical equivalent, we are going to prove the converse so that when you prove the converse, you can be able to establish by the principle of essentiality that P and not P is equal to F is law of complement by conjunctive statement. Conversely, F is equal to P and not P. You have seen that this F that is at the right side equation here has now become F at the left side equation here. Then P and not P at the left side equation here has now become P and not P at the right side equation here. We say that it is converse. Now let us prove the converse. So suppose F is equal to P and not P. We assume that the statement is true. And the statement is logical equivalent because whenever the left hand side of the equation is F, also the right hand side of the equation is also F. In the same vein, whenever the right hand side of the equation is F, also the left hand side of the equation is also F. Because the value of the each side of the equation is constant, always F. So we say that it's logical equivalent. Since it's logical equivalent, we are going to transform it to biconditional statement. That means if and only if F, if and only if P and not P. That means whenever the left equivalent is false, also the right equivalent is also false. Whenever the right equivalent is false, also left equivalent is also false. So whenever you make a statement, there's no possibility of getting falsity, always truth. You say the statement is tautology. Is tautology. Being justified by logical equivalence. Being justified by logical equivalent. Being justified by logical equivalent. We continue. Say if and only if and only if, or let's continue to this side. If and only if, since this biconditional statement is topology, that means if and only if P and not P is topology, we can also transform it to conditional statement and it will still preserve tautology. That means F implies P and not P. This means that whenever an antecedent is false, also the consequent must also be false, because we have only constant false in this antecedent and also constant of in this consequent when you evaluate it. So whenever F implies F is always tautology. So we say that statement is tautology. Statement is tautology. Being justified by logical implication. Being justified by logical implication. Now, since F implies P and not P is topology, we then conclude that F exists. That means F is logical, is proper implication of P and not P. That means it is certain that F exists. Since F is proper implication of P and not P, we say that F is logical implication of the consequent P and not P. That means if and only if F is if and only if F is logical implication of P and not P. F is logical implication of P and not P. Since F is logical implication of P and not P is true, also this must also be true. So if and only if F is equal to F, F is equal to F. That means logical implication is equal to itself. It is true that logical implication is equal to itself. And if it is so, it is logical equivalent. Because whenever the left hand side of the equation is F, also the right hand side of the equation is also F. Whenever the right hand side of the equation is F, also the left hand side is also is also F. You say it's logical equivalent, being justified by identity. That means the sameness identity. The sameness. So if and only if, or let's continue with it, if and only if F is equal to, that means F now is now, F is equal to, this F now is equal to negation. That means not bracket is equal to not bracket P or not P. If you look at this F is equal to not bracket P or not bracket P or not P. That means the negation of law of excluded value is equal to F. Because when you relate this statement, when you relate it, or when you relate this one, P or not P, to give us truth throughout and tautology throughout. When you relate it, to give us contradiction throughout. To give us contradiction. And contradiction is equal to F. So F is equal to not bracket P or not P or not P. Being justified by negation of law of excluded middle. Law of excluded middle. You got to decide. So if and only if F is equal to P and not P. Not bracket P or not P is equal to P and not P, being justified by De Morgan's law. P not bracket P or not P is equal to P and not P by De Morgan's law. Being justified by De Morgan's law. We have now proved the converse. We have now proved the converse. We then conclude, say, thus, F is equal to P and not P. Since we have not proved the converse, we then establish by the principle of essentiality that P and not P is equal to F is law of complement by conjunctive statement. We then say, therefore, P and not P is equal to F. We have now proved the law of complement. That means P and not P is equal to F is law of complement. So it is true that law of complement exists. So at this juncture, we withdraw our curtain. Thank you, viewers.